morning, everyone. Welcome to lecture number 33. Yeah. So, just to mention, last lecture's material was from Avram Blum's notes. I think notes number 6. Okay, so it's there in the Google Drive. Today's lecture, the first half will be Knapsack will be from Blum's notes, and shortest path will be from Jeff Erickson's book. Okay. Yeah, similar exposure is there in CLRS. I somehow like the exposition in Jeff Erickson. Probably CLRS is more detailed than Jeff Erickson's, but Jeff Erickson's is more intuitive, okay, rather than technical. Okay, so in the last lecture we looked at dynamic programming. So this paradigm is also kind of similar to greedy in the sense that it uses optimal substructures. So typically derivable from a recursive algorithm. Okay. What we call as memoized version. But it's not always the case. I mean, you need not have in many cases the recursion may not yield dynamic programming. You may have to do modification and so on. Particularly in the shortest paths example, we'll be doing that. So here, so the optimal substructure is kind of essential, but it's not exactly like the greedy matroid structure. It need not be greedy matroid structure. Other kinds of substructure properties are also good enough here for dynamic programming. So today we are going to see one more example, which is similar to, so in the last lecture we saw Fibonacci as a very toy example, the problem of computing Fibonacci number, and then we saw longest common subsequence. Yeah, just so yeah, the problem here is like given two strings x and y, so you want to compute longest common subsequence between them. So this problem is closely related to something called the edit distance of strings. Okay, that is so from string x to string y. So what is the number of edits that you need to do? Minimum number of edits so that you get string y. So edits are change a letter, change, insert, delete letters. Okay. So for example, from Apple to, let's say, app. Okay. So you need to delete these two letters. Okay. Say Cape to chapel. Okay. So you need to insert. So this is insertion. This is insertion. This is insertion. So you have to insert 3 letters here. So the edit distance is 3. Okay. So the edit distance is 2, and so on. Okay. Yeah, so I'll just leave it to you to read more about it. So for example, in Blum's notes, there is a connection between these two. And in Jeff Erickson's book, the chapter on dynamic program contains a complete treatment of edit distance problem. It gives a dynamic programming algorithm. But the relationship between longest common subsequence and edit distance basically, sorry. yeah, basically gives you a dynamic programming algorithm via longest common subsequence too. See, the idea is once you have a longest common subsequence, then what you do is you just remove and add letters so that you get the other word. Okay, so then the distance basically length of the word minus longest common subsequence plus whatever you need to add for the other. Okay, so I will not really go into the detail of it, but I would like to say that these problems are very well studied. So they are basically motivated from computational biology, where the main challenge is DNA sequencing, where you can imagine the strings representing as DNA. So when you want to match two DNAs, so what they want is either, I mean, mostly it is about the edit distance between the two or the longest common subsequence. Okay. So yeah, so we'll leave this at it. So for reference, read Jeff Erickson's book, Jeffy book. Okay. Chapter on dynamic programming. So today we'll see another example, very common example for dynamic programming. So here the task is the following. We are given n items. Okay. So for these n items, there are two parameters, size and value. Okay. So size says, okay, what is the volume or size of the item if you pick that item. Value is what is the profit that you make. Okay. The objective is to pick a subset of items such that your value is maximized, but it should be within the size. So you can just imagine you have some set of n items and you have a container of some fixed volume. Okay. Now you can imagine this is a task of a shipping company or a courier company. So they want to load objects into the container in such a way that their value or profit is optimized. So the revenue earned for each item is fixed as VI. So you want to choose the best fit subset, but it should be within the capacity. Okay, so the volume of the container should not be exceeded. So let's start with a simple example. Let's say items are 1, 2, 3, 4, 5. Okay, so value and size. Okay, say 10, 15, 12, 6, 19, 20, 30, 25, 20, say 50. Okay. Now let's take S as a capacity as, let's say, 40. Okay. So within 40, or maybe let's take a bigger value, say 50. Okay. So within 50, what is the maximum volume that you can get? Okay. So let's look at possibilities. So possibility 1, value. Okay. So include only 5. The value is 90. Okay. But instead, if you choose, let's say, 1 and 2, value is 25. Okay. Instead, if you choose 1 and 3, so this is within the size limit. Okay. So their size is 20 plus 30 here. So size is 50. So here size is 45. Value is 22. What are the other possibilities? 2 and 4. Value is 21. Is there any other possibility here? 1 and 3, 1 and 4. 1 and 4 is also a possibility, right? 1 and 4. Value is 16. to 4 is also a possibility. Done. Right? So now what is the best solution? What is the maximum value solution? 1, 2. By the way, I'm audible, right?
Yes, sir.
Yes, sir.
Okay, okay.
Yes, sir.
Yeah. Okay, so this happens to be the best solution. Okay, the maximum solution. So see, there are. So what is a brute force approach? So the solution here is a subset. You run through all possible subsets. Okay, I just leave it to you as an exercise. So let 1 to n be a knapsack instance. Let I be set of all solutions 1 to n such that summation I in A Si is less than S. Okay, is 1 to n I a matroid? So you just overcome violating the empty set axiom. So you can just imagine empty set is also a solution. Of course, this satisfies. So yeah, it is not required. Okay, so it satisfies the condition. So empty set is also independent in this definition of independent set, as well as it's also closed under subset. If a subset of say A also satisfies, I mean, if you pick any subset of A, it also satisfies the size restriction. Okay, but however, you can see that there may not be an exchange axiom that is respected. I mean, the exchange axiom may not be respected. You can easily get examples. So this happens not to be a matroid. So I just leave it to you to work out the details. Okay, so greedy algorithm won't work. Okay, so in fact, this is not just a rare exception. In fact, for most of the problems, greedy algorithm does not work, because greedy algorithms require that structure, which is like matroid structure, for example. I mean, most of the greedy algorithms have matroid structure. Then, yeah, very rarest of the problems that we consider in practice have that structure. Okay. So instead, we'll try a simple recursive solution. Okay. And then we'll see how to convert this into a dynamic programming solution. Okay. So a recursive formulation. So let's say we have items 1 to n. Okay. So their values v1 to vn. Their sizes s1 to sn. Okay. So just to be concrete, so sorry, the brute force solution, right? What is a brute force solution? Output is a set. You run through all possible subsets, right? So the brute force solution, let's call it as brute force or naive solution for all t subset of n. So set max as 0 if summation I in t si less than equal to s and summation vi I in t is greater than max, set max equal to summation vi I in t. Okay, maybe solution as empty set, so solution as t. Okay, So how many subsets of 1 to n? Exactly 2 power n. So this algorithm will run for 2 power n steps. Okay, so 2 power n into cost of this computation, we'll take it as unit cost. So then it is order of 2 power n. Okay. So now let's try another recursive formulation. Okay, which of course with the naive implementation it will also lead to the same kind of complexity, but nevertheless, I mean, it helps us to set up dynamic programming, which could be far efficient. So one thing is, if you look at the last item, see, any solution, either it contains this item or it does not contain, right? Yeah. So any solution either it contains n, item n, or not. Okay. So now what we do is we recursively compute. Okay. So if we were to include the last solution, the last item, if sorry, so nth item is included, then value is Vn plus, so the remaining should be a solution for the reduced instance where you exclude the last item. Okay, so this is n minus 1, value of solution for 1 to n minus 1. But then what is the capacity? So if we are deciding to include item nth item, then the capacity will go down by the size of nth item, right? With capacity or size s minus sn. If nth item is not included, then value is value of solution for 1 to n minus 1 with capacity s. Okay. Now what we do is we recursively solve this. So we recursively compute value of these solutions for these instances. Both instances have exactly the same number of items, but the capacities or size bounds are different. Now you take the better of the two. Okay, so that is a straightforward recursive algorithm. I'll just show you the algorithm here. So let's call KSNS as a knapsack instance with n items, S as a capacity, size. Okay, so if the base case is just no item at all, so if there is no item, then the value of the solution is also 0. Okay. Now again, primitive check is, or sanity check is, if value of the nth item is greater than the capacity, right? No point having that item. You cannot have that item at all. Okay. So then you as well return solution for the instance 1 to n minus 1, that is items 1 to n minus 1 with the same capacity. Else what you do is you compare these two. So these are the two cases that we have discussed. So look at Vn plus the solution of instance with items 1 to n minus 1, but the capacity reduced as per the size of nth item. And then the second recursive call is first n minus 1 items, but with the same size. Okay, so return result. Okay, so let's just try to make the recursive call. So I hope the algorithm is clear. We'll just run the algorithm on this example. Okay, so let me erase this. Okay, I will have to keep this. Okay, KS 550. Okay, so if you want to include the item number 5, then the S value becomes 0, right? So the first branch is returning you 19. Okay, so the second branch is, so 5 included, 5 not included. When 5 is not included, so you have capacity as 50. Now either to include 4 or not. So 4 included, 4 not included. Okay, if 4 is included, the capacity goes down by 20, so the capacity becomes 30. Value added is 6, so 6 plus KS 3, 30. Okay, now again either include 3 or not. 3 not included. If 3 is included, this becomes 28. So the only thing is, now if you see, n won't be 0. Okay, n won't be 0, but what is the value of s in this case for this subsequent call here? You have included 4 and 3, so value of s will be 5 here. Okay, s will be 5. So then the subsequent recursive calls, the value of Sn will be exceeding 5, so it will just return. So it will go to n equal to 0, it will return 0. So the solution will be 28 here. Sorry, capacity is, how did I get 28? 18, right? Sorry. Did I miss any hands? Okay, no. Yeah, any
So you missed 3, 4, sir. The possibility of 3, 4.
3, no, this is what here it is, right?
So no, not in the tree, sir. In the list of possibilities.
Oh, here. Okay, sorry. Okay, so 3, 4, 3, 4 I didn't include. Okay, yeah, good. Yeah, 3, 4. Value is 18, right? Yeah, thank you. Anything else did I miss? 1, 2, 1, 3, 1, 4, 2, 4, 2, 3. 2, 3 is included. 2, 3 is also not included, right? 2, 3 cannot be included. Yeah, 55. Okay. Okay, so here 3 included, we get 18. If 3 is not included, then either we'll include 2 or not. So 2, 2 not. Okay, so 2 is included, this will be 21. 2 not included, 1 included, 1 not included. 1 not included will give me only 6. 1 included will give me 16. Okay, and yeah, from here I'll draw it this way. Now whether to include 3 or not. If you include 3, 3 not included. So 3 included, this will be 12. Now 2 included or not. If you include 2, this is violating. It won't give you anything, and I mean it will give you 12 only. And 2 not included, we will have a question of including 1 or not. 1 not included will give 12 only. If 1 included, it will give us 3 included, 22, right? Okay. Yeah, so far we didn't get to the optimal, but I hope the run of the algorithm is clear. Okay, so now if we expand this further, what was our solution? Solution was 1 2, right? So here 2 will be included. So once you have 2 included, capacity becomes 20 and the value becomes 15, and then again 1 will be included. So then value becomes 25. Okay, capacity becomes 0 and n becomes 0. So that will be the one that will be picked. So basically the recursive algorithm traverses through these trees, looks at these values, takes the maximum. Okay, so that's essentially how it works. So what is the complexity of this algorithm? So T of n be the time complexity of this algorithm on an instance with n items. What is the recursion that it can give? A recurrence relation? See, one thing is it also depends on, you can say that, okay, it also depends on this Sn. Let's not really worry about, let's only worry about this parameter, okay? So let's imagine that the sizes are chosen really bad, okay? Such a way that, I mean, this will go into the worst case. So in the worst case, what will be the call? See, best possibility will be you make only one call, okay? But that is not always given, right? So in the worst case, this will be 2 into T of n minus 1 plus what is the time that you spend here? You may have to do one addition, two comparisons, and that's all, right? And one subtraction. That's it. Okay. Also, if you count this decrement, so this is order 1. Okay. So this is order of 2 power n. Exercise. Prove this. Okay. So solve the recurrence. I mean, it's fairly straightforward to solve this recurrence. This will solve to order of 2 power n. Okay. So every time you will have constant work done, but 2 recursions of instances of size n minus 1. Okay. So compared to the naive algorithm, which also had brute force algorithm, which has also had complexity of 2 power n, order of 2 power n, in fact, this won't change much. Okay, so if you are really pedantic, you can say that, okay, this for this I'll have to add. So size of t could be as big as n, so there could be n additions. So this could be n into 2 power n, whereas this one is some constant times 2 power n. Okay. Nevertheless, it really does not matter as such. So the complexity is comparable. Okay, so it's comparable to the brute force. So it does not really save us anything. So here comes the crucial observation. So let's just look at this tree once again. Okay, so Ks Ns. Okay, so what are the calls that you're making? Ks Ns prime, Ks N, sorry, not N, sorry. Ks n minus 1 s prime, whatever that s prime is s minus s1, sn, sorry. Ks is Ks n minus 1 s. Okay, so you keep on making these calls. Okay. So what does this time complexity tell us? What will be the size of this tree? See, for any recursive algorithm, right, if you draw the recursion tree, that basically gives you the time complexity, right? Number of nodes in the recursion tree times time spent at each recursion level is your time complexity. So time complexity is order of 2 power n. So that means this tree will also have 2 power n nodes. right? But if you look at this tree, each node can be labeled by the call that we make, right? So what is that label? KS n comma s, or to be more precise, each node can be labeled by KS ij for some ij. Do I make sense? So if you look at this example too, so here for each call, the parameter, you can label the node by the parameter that you make for that call, right? Yeah. So how many possibilities? So the first parameter can be from 1 to 5. The second parameter can be any number less than 50, less or equal to 50. Okay. So the crucial observation is the labels of these trees. So the ij values, so first point is for any node, there is an ij such that the tree is labeled by ksij. Okay. But the number of labels is constrained by the value of n and s. Okay, so observation is, let this be the recursion tree. It has 2 power n nodes. So the observation is for any node in the recursion tree, okay, there exists an I from 1 to n and j from 1 to s such that it is labeled by ksij. So what do I mean by ksij? So the node in the tree corresponds to the call for the recursive function with parameters I and j. So that means it needs to compute this value. But how many such labelings are there? How many such labelings?
2 power n.
Okay, how many
N2S.
such distinct labelings? Yeah, how many? I mean, you mean labelings should be equal to the number of nodes, which is 2 power n. Okay, but how many distinct labelings are there?
Yeah, N into S.
N into s, right? So number of such labels. So number of distinct labels is n into s. So that means what this recursive algorithm does is recomputes the values unnecessarily, right? It keeps on recomputing the values. So if s is much smaller than say 2 power n, then it's actually recomputing a lot of values unnecessarily. Like we did for longest common subsequence problem, LCS problem, we can do memoization. We can store the values as and when they are available. Okay, so we can modify this recursive algorithm by using a global variable to store the values as and when they appear. Okay, so that's pretty much what we have done in the last lecture. It's the same thing here too. Okay, so what you do is you initialize, say array is the value, array is the 2D array where we will store these values. So you initialize everything to say -1, some value we'll call as unknown. Okay, so now algorithm is the same. So what we do is at first we check if the value is known. So this is checking if the value is known. Check if the value is known. If so, return it. That means you avoid recursion. Okay. Otherwise, it's the same. So you check for, sorry, check for S, the last item has size greater than s or not. Else, you compute recursively the best possible value by taking the max of two recursive calls. For one, you add the value of vn. But after you get the result, you update the array content. So you imagine that array is a global variable here. Okay. So you update array ns to the result value. So we are assuming that item values are non-negative. Okay. Item values are positive. Okay. So then unknown can be treated as -1, or else some small value or large value can be treated as unknown. Okay. Some fixed value, and you return the result. This is all the modification is. Okay. So how does it affect the complexity? Okay, maybe here. So let's just look at this. So if you look at any ij, so how many times we will make a call for case ij?
At most.
At most once, right? Why is that? So if I say, for example, I have n and s, so I is n and j is s. So the subsequent call here either has n, so it in fact has n-1. So you are not going to have I, right? But the value of s could be the same. Okay, but however, the value of I certainly changes. Okay, but when you return, so all subsequent calls will not have the same value of I. Okay, once you return, you will update the value of array ij or array ns in this case. Okay, so once you make this call case ij, once you return, so here array, sorry, array ij will be the value. Okay, so some value, so it will be known. Let's write it as known. So anywhere else, if you are going to make this call, you will never make this call. So once you have this call, you will immediately return the value array ij. Okay, so everywhere is case ij will be array ij. Okay, or in other words, for each ij, there will be at most one node labeled case ij. Okay, so for the memorization algorithm, for all ij, there is at most one node in the recursion tree that is labeled case ij, such that it makes subsequent recursive calls. See, all others, they will also be labeled case ij, but they will not make subsequent recursive calls. Okay, therefore size of the recursion tree will be how much? All other cases you will be terminating immediately. Okay, so you will be terminating immediately, so you will be just returning the value. Okay, you will not be making any further subsequent recursive calls. So therefore time complexity will be order of n times kernel, sorry, n times s. I'll leave it to you to prove it precisely, what is a precise constant and so on. But I hope the intuition is clear. It's very similar to what we did for LCVS. In fact, most of the dynamic programming algorithms, they follow this kind of structure, okay? But when we present it, we may not present it the recursive way, okay? Because like I said, most of the cases, recursion is, the overhead for recursion is very much, okay? But pedagogically, recursive algorithms are easier to present. They are easier to present, easier to implement, but not very easy to analyze. Complexity wise, they are not certainly better than iterative versions. Okay. Yeah.
Hello.
Yes.
Can you go to that slide where we were talking about the complexity?
This one.
Yes, sir. Sir, can you explain this statement? I did not understand the statement. I understood how the algorithm is better, but
yes,
this particular statement.
Yeah. So see, we are just counting the nodes labeled by case ij, which makes subsequent recursive calls. There is only one which makes subsequent recursive calls. Okay. Everything else, it will just terminate. The recursion will terminate here. The recursion will terminate here because you will be you will not be making subsequent recursive calls, right? Once array ij is known, you will not make further calls.
Okay, so the recursion trees number of nodes, you are saying intuitively it is the number of possibilities of n and s.
Yes, not intuitively, precisely. So the number of nodes that make subsequent recursive calls is order of ns. In fact, n times s. That's all.
So we got better from 2 power n to ns.
Yes, that's all.
Okay.
Yeah.
Excuse me, sir.
Yes.
Sir, here, if the value, if array n of s is not unknown, then we return the saved value.
Yes.
But shouldn't we first check if s of n is greater than s? Shouldn't that statement come before?
Oh, that is basically a sanity check, right? This, yeah, no, it may not come before. So this is only a sanity check, right? So you see, first thing is you need to see if you write no, there is also another problem if you move this up, okay? So you'll be making a recursive call here, right? Which could be unnecessary because you might have the value already. If you have the even in the case when Sn is greater than s, there will be a solution, right? There will be a value that you get. So if you make this recursive call before, it's going to be troublesome. So this check preempts any further recursive calls. If the value is available, don't bother calling again. Don't bother making any recursive calls. So this Sn greater than s is it just tells us, okay, you cannot include the nth item. That's all, right? So you cannot. If you make it, the complexity changes.
Okay.
Yeah. Okay, good. Okay, so in the remainder of the lecture, I'm going to discuss about shortest paths problem. Okay, I'll just state the problem. So nice thing about, so the next 2 to 3 lectures we'll be discussing on shortest paths. Okay, so nice thing about shortest paths is there are cases which admit greedy algorithms as well as dynamic programming. Okay, so it's kind of, many solutions are kind of mix of dynamic programming and greedy algorithms. And it's one of the crucial problems which has lots of applications, okay, wide applications, and they're also widely studied, okay, lots of algorithms, and yeah, so in different contexts, okay, so there are distributed algorithms, parallel algorithms, and so on. So in every context, there has been a study of these problems, okay. I'll state the problem formally and tell you a context where it is applicable. Of course, that's only one of the contexts. There will be lots of other contexts where it is applicable. Okay. So here we'll assume that we have a directed graph, okay, with edge weights. Well, the same problem is also applicable for undirected graphs. Okay. Now, in many cases, you'll also be given two nodes. Say this is for source, this is for terminal, okay, which are distinct. Now, a path from S to T is a sequence of distinct vertices, say S, V1, etc., Vk to T, such that these are edges. S to V1 should be an edge, V1 to V2 is an edge, etc., etc., etc. Okay. And weight of the path is sum of the weights of the edges. Okay, that is weight of S, W1, etc., etc. So I'm assuming Wt is the weight function. A shortest path is one which minimizes the weights. Okay, so I'll give you an example here. So if you take this graph, so let's take this as S and this as T. This is S and this is T. Okay. Now, what is the shortest path from S to T? So this path takes 2, 3, 3, 6 to 8 for 12. This path 2, 3, 5, 5, 6, 11. Is there anything better than that? 6. This is 14. This will be higher. This will be higher. So the best path is this. So this is the shortest path from S to T. Okay. So you look at all possible paths, the one which minimizes the weight. So what is the total weight of this path? It's 2 plus 3 plus 6, 1 plus 5. Okay, so that is 11. Whereas any other path will have larger weight. So 3, 3, 6 plus 4, 10, 12. This path has 12. This path has much higher. And is there any other path? This path has much higher, and so on. Okay. So one thing is, I mean, if you have an undirected graph, you can just imagine it as a directed graph with adding two edges this way. Say, for example, this. Okay. But in which case, usually the weight has to be the same. So in this case, it is not. So here I have put 6 as a forward edge weight, and this is a reverse edge weight. Okay. Now, there are many scenarios where this problem is useful. So one of the examples you would have seen is road networks. Okay. Suppose we want to drive from IIT campus to, say, the central railway station. So how to compute the shortest route? Well, these days, even you can ask a small kid who knows how to use a smartphone, he or she will just say, okay, use Google Maps. Okay. But that we are not looking at the user end solution. We want to develop solutions. So we want to understand how it is done. Okay. One natural way is, I mean, there are multiple ways of representing it. You can model road network as a graph. Okay. So for example, you can have vertices representing junctions of 2 or more roads, intersections of 2 or more roads. Okay. And edges representing direct roads between 2 intersections or junctions. Now you can put weight of an edge either as distance or distance plus congestion, some function of distance plus congestion. Okay. So the cost of the travel, or when you say shortest, it could be with respect to time. So you can just say the time required to travel from point A to point B is this. Now what we want is shortest path. So what we want is a path from node representing IITM to the central railway station, where such that the total weight is minimized. That is, total travel time is minimized. If you want distance, then this will be just distance. If you want just about congestion, some parameter with respect to congestion, so then this will be the shortest path will represent the path or the route with the minimal congestion. Okay. So this is one example. I mean, there are lots of examples of shortest path, and it's one of the central problems in the study of algorithms. And it's also fairly interesting. There are like different kinds of algorithms that can be developed. Okay. In this lecture, we'll look at certain properties of the shortest path problem. I'll take a couple of more minutes. Okay. So one important thing is shortest paths have optimal substructure. So what do I mean by that? So let's take our previous example. Let me draw the shortest path here, maybe a different color. So let's say V1 to Vk is the shortest path from V1 to Vk. So this is V1 and this is Vk. Okay. Now the interesting part is, so this represents, or this shortest path has the following substructure property. If you pick any two nodes along the path, okay, so the stretch of the path will also represent the shortest path between these two nodes. So let's say I take Vi as A and Vj as B. Vj as say C. Okay. So then this path is also, if you take this stretch, this is also shortest. Okay. So if you take any subpath of it, it is also optimal. It's also minimum. See, one thing is the shortest path may not be unique in a graph. Okay, in this graph, it probably for S and T, it is unique, I think, but in general, it need not be. Okay, so what we say is, if you walk along the path, so any intermediate walk is also optimal. Okay, so this is optimal substructure property. Okay. So this is not exactly the greedy optimal substructure, because the problem here is when you have a path, there is a natural ordering. Okay, so many of you would have got this quiz one question, right, about induced paths or paths. Okay, so the problem there is, I mean, mathematically you'll have to show that, okay, the exchange axiom does not hold and so on. But the problem there with the notion that I had given, a subset as a path, is there is an ordering which is hidden. Okay, so the ordering is important. So that way, this is not a greedy kind of substructure property, but still it is a substructure property. If you are talking about subpaths, they are all optimal. Okay, so this property is true. It's irrelevant to what S and T is. So it can be any V1 to Vk. So if you take any shortest path, any subpath of it will also be shortest path. Okay, so that is one of the important properties of shortest paths. Okay, so maybe I should stop here. So what this gives is this optimal substructure property. So if you just say color the edges which participate in shortest paths. Okay, so let's say I'm imagining S as one single source. I'm interested in all shortest paths from S. Okay, say shortest path from S to G is this, S to E is this, and F to E is this. Sorry, F I'm not including. E to D. So S to D is this is the shortest path. 2, 3, 5, 3, 8, 6, 8. One of that. Okay, so I can take this as well. Okay, and what else is remaining? S to F. S to F is 2, 5, 6. One of that. Okay, so you can take this as the shortest path. Okay, so this gives us a tree structure. If you look at this, for any node V, so this green edges represent a shortest path from S to that node. Okay, so when you fix a source and you look at all nodes and their shortest paths, and if you draw edges, you can draw edges in such a way that there is a tree. Okay, so that is an interesting structure. Offline, I'll just want you to think about this tree structure and MST. We'll be considering this formally in the next lecture. Okay, I'll stop here now. Srinivasa, can you stop the recording also?
Yes, sir.
Yeah, thank you, Srinivasa.